For more physics-related videos, please subscribe. Welcome to Stellar Physics 5a. In this video, I will cover the basics of nucleosynthesis. Now, nucleosynthesis and nuclear physics in general is a pretty complicated topic and requires a good understanding of quantum mechanics. In the first video in this series, Stellar Physics 1a, I stated that you would not need to know any quantum mechanics to get through this series on stellar physics. So in this video, there won't be any in-depth calculations. Instead, I'm going to take more of a qualitative approach to try to give a good overall picture of how nucleosynthesis works. As such, I rated the physics level in this video as intermediate. So let's start off with nuclear binding energy. Nuclear binding energy can be thought of in two ways. They're both equivalent. You can either think of nuclear binding energy as the energy released during nuclear fusion, or as the energy required to break up a nucleus. So, how does nuclear fusion work? We have two nuclei, which are made up of protons and neutrons. A is the total number of nucleons, so it's the sum of the protons plus the neutrons. Z is the charge of the nucleus, so that's the number of protons. And N is the number of neutrons, which have no charge. These two nuclei come together, they fuse into a larger nucleus, and in the process they release some energy. That energy will be released in the form of some kind of particle or particles. Which particles will depend on the specifics of the nuclei being fused. The energy released will be the rest mass energy difference between the two initial particles and the final particle. Now, nuclei are positively charged because they're made of protons, which have positive charge, and neutrons, which have no charge. And positive charges repel one another according to the Coulomb force, or the electrostatic force. This force is proportional to the charge of each initial nucleus. So, Z1 is the number of protons in nucleus 1. E is the charge of a proton, which is the same as the charge of an electron, just positive. And Z2 times E is the charge of the second nucleus. The Coulomb, or electrostatic force, is also proportional to 1 over the separation distance between the two nuclei. Or I should say, the separation distance squared of the two nuclei. And K here is just a constant, it's called Coulomb's constant. So if these two nuclei are repelling one another, why do they come together and stick in the first place? Well, the reason they bind together is because of the strong nuclear force. And as suggested by the name, the strong nuclear force is very strong. So it wins over the Coulomb force. Well, actually, it only wins if the nuclei are very close to one another, because while the strong nuclear force is very strong, it's very short range. Whereas the Coulomb force is a long-range force. So how close do these nuclei have to come together for the strong nuclear force to win? Well, they basically have to be touching one another. So about the radius of a nucleus. It's easier to think of this in terms of energy rather than in terms of forces. So I'm going to plot the potential energy of the nuclear force and the Coulomb force as a function of the distance between the two particles. The potential energy associated to the Coulomb force is almost the same as the Coulomb force itself, except that in the Coulomb force we have a 1 over r squared, and in the energy we have 1 over r. The potential energy of the strong nuclear force is basically zero everywhere until you get to about the radius of a nucleus, and then you get this very deep potential energy well. And the width, as I said, is about the radius of a nucleus, so r naught is the radius of a proton or a neutron, and a is the atomic number, which is the number of nuclei. So why does this go as a to the 1/3? Well, the volume of a nucleus will be the volume of a nucleon times the number of nucleons. And there are a nucleons in the nucleus. The volume is proportional to the radius cubed. So we take the cube root to get the radius, which means we're taking the cube root of a, hence a to the 1/3. The depth of this potential well will be the same as the energy released. To get the total potential energy of these two forces combined, we just add these two curves and get a curve that looks something like this. Now, this situation is completely analogous to a ball rolling up a hill and falling into a hole. If the ball doesn't have too much energy, it'll roll partway up this hill and just roll back, which means the two nuclei come close together and then they turn around and repel one another. In order to get the ball into the hole, you have to have enough energy to get over this hill, and then it'll happily fall in the hole, which is where it would like to be. Once it's in the hole, it's hard to get it out of the hole. Now, if this were actually a ball rolling up a hill, you would need to have at least enough energy to get up this hill in order to fall into the well. But in quantum mechanics, as long as you can get close to the top of this hill, there's actually a probability that the ball will just show up inside this well. And this is called quantum tunneling, because the idea is the ball doesn't have enough energy to get up the hill, so instead it just tunnels its way through the hill and winds up inside this well. If you want to get the ball out of the well, you have to give it back the binding energy so that it can then shoot up out of this well and roll back down this hill. And I should mention that the probability that the ball will tunnel through this hill will be greater the more energy the ball has. Of course, if the ball actually has enough energy to get up the hill, then the probability that it will wind up inside this well is almost 1. So that's basically how it works. You need to get these nuclei moving really fast so they can get very close, and once they're basically touching, the strong force will take over and win over the Coulomb force, and the nuclei will fuse. So what does it mean you need to get them moving fast enough? It means they have to have a lot of energy. So in order to get fusion, you need your gas to have a very high temperature. Alright, now that we have a basic idea of how nuclear fusion works, let's move on to what's called the semi-empirical mass formula. This is a formula for finding the mass, or the mass energy, of a nucleus with a given number of nucleons. So of a nucleus with atomic number A. So how are we going to find this? Well, we're going to picture the nucleus as basically a spherical bag full of nucleons. So in this bag, we've got a bunch of neutrons and protons all bumped up against one another. So what is the mass of this bag? Well, we have Z protons and N neutrons, so its mass will be Z times the mass of a proton plus N times the mass of a neutron, or mass energy if you prefer. But remember, all these nucleons are bound together, and in order to bind them together, we had to release some energy. So we have to subtract off the binding energy. Now we have to figure out what the binding energy is. Remember that the nuclear force is very short range. So if we take a look at a nucleon in this nucleus, it'll be touching other nuclei on all sides. So we'll have a binding energy associated to each of its neighboring nucleons. Since there are a total of A nucleons in this nucleus, the binding energy will be some number times the number of nucleons A. But actually, we've overestimated this number. While a nucleon inside of this nucleus, or in the center of this nucleus, will be surrounded on all sides by other nucleons, the ones on the surface are only surrounded on one side by nucleons. So they're not going to feel the same binding energy because they don't have as many neighbors. So we need to correct for the fact that these surface guys aren't as tightly bound. So we're going to add a term for the surface term. This constant, by the way, little a sub v, I've indexed sub v because this term is called the volume term, while this one is the surface term, so it's little a sub s, and it's proportional to capital A, the number of nucleons, to the 2/3. Why to the 2/3? Well, we found already that the radius of the nucleus is proportional to a to the 1/3, and the surface area is proportional to the radius squared, so a to the 1/3 squared gives you a to the 2/3. Now that covers the binding energy for the strong nuclear force. But there's also the electrostatic force, because this nucleus has a bunch of protons in it, and the electrostatic force between the protons wants to blow this nucleus up. So we need another correction term for the potential energy associated to the Coulomb force. Let's take a look at one of these protons. Let's say this guy. It will feel a force from every other proton inside this nucleus. So there will be an energy associated to all of the other protons acting on this proton we're looking at. That potential energy will be the charge of our proton times the charge of all the other protons acting on it. Since there are Z protons, there are Z minus 1 other protons, and it will be proportional to 1 over the distance between our proton in question and the other protons. What is that distance? Well, it's going to be roughly the radius of a nucleus, so proportional to a to the 1/3. Now this energy is the electrostatic energy for one of the protons in this nucleus. Since there are a total of Z protons in the nucleus, we multiply this by Z to get the total electrostatic energy of the nucleus. So we can now write down a correction term that's going to be some number, A sub C, C for Coulomb, times Z minus 1 divided by a to the 1/3. If you're enjoying this video so far, please consider liking and subscribing, and maybe share it with a few friends. Now, it turns out there are two other terms in this formula that are a result of quantum mechanics, and they're a little bit subtle. We said earlier that binding energy is completely analogous to a ball inside of a well. Well, here we have two kinds of balls. We've got protons and neutrons. So we can draw a well for each of these balls. Now, it turns out in quantum mechanics that if you have a ball inside of a well, it can only occupy certain energy levels. For a ball inside of a well, the energy is basically its height. So saying that the ball can only occupy certain energy levels, it basically means that we have a ladder inside of the well, and the ball has to sit on one of the rungs of the ladder. It cannot be sitting between two rungs. So let's draw a ladder for the protons and a ladder for the neutrons. Now we have to place the protons and neutrons on these ladders. There's one more thing we have to consider here before we can do that. If you've been following the series, in Chapter 2, where I went over thermodynamics, and specifically in Stellar Physics 2a, I explained that there are two kinds of particles in the universe: fermions and bosons. And the main difference between them is that for bosons, you can place as many bosons in a given state as you'd like. Whereas for fermions, you can only put at most one fermion in a given state. Two fermions cannot share the same state. Well, it turns out that both neutrons and protons are fermions, so they can't all be in the same state. Keeping that in mind, we're now going to populate this ladder, starting with the protons. Nature wants to minimize energy, so our first proton will be placed at the minimum energy possible, which will be the bottom rung of this ladder. Now, protons and neutrons have what's called a magnetic moment, which basically mean they're like little magnets. And that magnet can either be pointing up or pointing down, which corresponds to two different states. So, for a given energy state, I can put two protons, one with its magnet pointing up and one with its magnet pointing down. And that's it. I can't put any more protons at this energy. I have to go to the next rung up in the ladder, where I can also put two protons. For the neutrons, it's the exact same thing. I can put two neutrons on each rung of the ladder. Okay, let's remember what we're doing here. We're trying to find an equation for the mass of a nucleus with a number of nucleons. In this example, I've got a total of 8 nucleons, 4 protons and 4 neutrons. But there are other ways to get a nucleons. I don't have to have the same number of protons and neutrons. So for example, I could have only 3 protons and 5 neutrons. Let's take a look at what our ladders would look like in this situation. For the protons, I'm only going to have 3. So the first 2 will go on the bottom rung, same as before. And on the second rung, I only have 1 more to place. For the neutrons, I have 5 neutrons now. So the first 4 will be the same as the previous ladder. And the 5th neutron has to go to the next rung up in the ladder. Now let's compare the energies of these two situations. To make the numbers easy, let's just say that each rung has an energy of 1 above the previous rung, starting with the bottom rung having an energy of 1. What's the total energy of this configuration? On the bottom rung, we have 4 nucleons, each with energy 1, so that's a total energy of 4. On the second rung, we again have 4 nucleons, but they each have an energy of 2. So 2 times 4 is 8, plus the initial 4 gives me a total energy of 12. In this situation, I again have 4 nucleons on the bottom rung, giving me an energy of 4. On the second rung now, I only have 3 nucleons, so 3 times an energy of 2 gives me 6, plus the initial 4 is a total of 10. And then I have 1 nucleon at an energy of 3, giving me a total energy of 13. So this situation has more energy than this situation, despite the fact that they have the same number of nucleons. With a bit of mental effort, you'll realize that the lowest possible energy is when you have the same number of protons as neutrons. So now we need a term in our semi-empirical mass formula to account for the fact that the more asymmetric the number of protons and neutrons are, the more energy we have. I'm not going to derive this term because you have to know something about quantum mechanics to do so, so I'm just going to tell you that it's equal to some number, A sub capital A. This capital A, by the way, is not the atomic number. It stands for asymmetry because this term is called the asymmetry term. So this term, it turns out, is proportional to n minus z squared divided by the total number of nucleons. So we can see that the bigger the difference between n and z, so the bigger the difference between the number of protons and neutrons, the bigger this term gets. And if n equals z, this term is 0. We have one more term to add to our formula, and it's also quite subtle. In this situation, we have an even number of protons and an even number of neutrons, giving us an even number of baryons. In this situation, we also have an even number of baryons. Protons and neutrons are nucleons, but they're also baryons, so I may use baryons and nucleons interchangeably here. As I was saying, here we have also an even number of nucleons or baryons, but in this situation we have an odd number of protons and an odd number of neutrons. So in both of these cases, A, the atomic number, the number of nucleons, is even. There's one more possibility, which is that A is odd. So we have an odd number of nucleons. This could either be an odd number of protons and an even number of neutrons, or vice versa. Why does this matter? Well, recall that I said that our nucleons, both the protons and the neutrons, are like little magnets. And what do magnets like to do? They like to stick together with opposite poles touching, meaning they like to stick together with one magnet up and one magnet down. What does it mean when I say they like to stick together? Well, nature is always minimizing energy, so when I say they like to stick together, that means that bringing these two magnets, one up, one down together, is a lower energy state. So, whenever we have two nucleons coupled together, one up, one down, that's lower energy. So now let's compare these three situations. In this case, all of the magnets are coupled to another magnet. If A is odd, we have one free magnet. So this should have more energy than this one. And if Z and N are both odd, we have two free magnets. So this should be even more energy than this guy. So now, how do we quantify this? The way we do this is we're going to call this our baseline energy. So we're going to call this energy 0. Then we're going to say that this guy has an energy of negative delta E, where delta E is the energy difference between a coupled magnet and an uncoupled magnet. In this case, we have two uncoupled magnets versus one, which was our baseline energy. So we have an extra energy of delta E. Now we have to write this mathematically somehow into our semi-empirical mass formula. And the way this is written is by adding a term that's delta E times this number little delta, where little delta can be either -1, 0, or +1, depending on which configuration you're in. If Z and N are even, this is negative delta E, so we have -1. If A is odd, then delta is 0, and if Z and N are both odd, then delta E is +1. And that's it. That's the semi-empirical mass formula. If you have a nucleus with a given number of nucleons and a given charge, so number of protons, you can plug into this formula to find its mass. And recall that A is equal to Z plus N. So you don't need A, Z, and N. Having two of them will give you the third one. Now I said you could plug into this formula, but there's actually some numbers in here we don't know, which is all of these factors, A sub V, A sub S, A sub C, etc. We don't know what those numbers are. So how do we find those? The way we find this is empirically, meaning through measurement. We measure the masses of a bunch of different nuclei, and then fiddle around with these numbers until we get the best fit for the general formula. Now this entire derivation was a little bit hand-wavy, so this formula, while it works pretty well, is not super precise, but it at least gives us a picture of how the masses of different nuclei are determined. But actually, it does more than that. This formula will allow us to find which nuclei are stable and which ones are unstable. And that I'm going to do in the next video, where we're eventually going to find that the semi-empirical mass formula can be used to explain what's called the valley of beta stability. So here I have a graph of various nuclei where I've plotted the number of protons versus the number of neutrons, and the black squares are all the stable nuclei, and this is called the valley of beta stability. All of the other colored squares are unstable nuclei, and the color tells you the decay mode of that specific nucleus. So basically what happens is, if you have an unstable nucleus, say around here, it will decay from one nucleus to another, meandering its way around until it eventually decays into a stable nucleus. In the next video, we're going to use the semi-empirical mass formula to determine the conditions for nuclear stability. If you've made it this far, stay tuned for this video. Be sure to subscribe and hit the bell to be notified when it's released. Thanks for watching.